The integral test and P-series. So in the previous section, we learned what a series is. We also defined what we mean by a convergent series and a divergent series. And we took a couple of examples where we were able to actually find the exact sum of a convergent series. And particularly, I'm talking about the geometric series and the series sigma 1 over n times n plus 1. So it was a series which has telescoping sums. And in both instances, we were able to find a simple formula for the nth partial sum, right? Remember, the sum of a series is equal to the limit of the sequence of partial sums. So, but in general, it's very hard to find the exact sum of a series because it's not easy to find a formula for the nth partial sum. So as such, in this and the next few sections, we're going to develop a few tests that are going to enable us to determine whether a series is convergent or divergent without explicitly finding the sum of the series. Okay. One such test is the integral test, which is the main test of this section. So here are the details of the test. Suppose that the function, you're given a function f, which is a continuous function, positive function, and a decreasing 1 on the interval 1 to infinity. So three conditions: continuity of the function, positivity of the function, and the function being monotonic but decreasing on 1 to infinity. And suppose that the image of any natural number is equal to an. So the image of of n, where n is a natural number, is defined to be an. As such, under these hypotheses, you have the following: the series whose terms are the ans, those guys, is convergent if and only if the improper integral 1 to infinity f of x is convergent. Remember, when the function is positive, this expression may be thought of as the infinite region bounded by x equals 1, the function f and the x-axis. It's infinite in extent, right? The area may be finite, and hence the improper integral being convergent by definition. All right, so you have this two-way street between series and improper integral, obviously under these hypotheses. In other words, what the integral test is saying is that if this infinite region is finite, then this series is also finite. By the way, this is not saying they have the same value, right? They're both finite. This is what this is saying. If this is finite, then this follows. But this is not saying that they have the same value, by the way. Okay. And if this area is divergent, and the only way it's divergent is that this is infinity, then that's gonna diverge as well. Okay. All right, so here's the proof of the theorem. So what are we given? We're given a function which is continuous, positive, and decreasing on 1 to infinity. So the function looks like something like this, correct? The pink curve. I'm gonna create two figures, figure L for left, figure R for right, and I'm gonna look at those rectangles. On the left figure, I'm gonna look at rectangles where their height are the image of the left endpoint of that interval. Okay, so what are we doing? We have, we have we partition one n, this interval, into n subintervals, 1 to 2, right? Whose length is 1. So 1 to 2, 2 to 3, 3 to 4, etc., all the way n minus 1 to n. And we're creating rectangles where one of the dimension of the rectangles is always 1, the length of the interval, and the height of any rectangle is going to be the image under the function f of the right endpoint, correct? So what is this area here? Well, this area here is 1, which is this length, times this measure here. What's this measure? It's f of 2, right? It's f of 2. This height is f of 2. Well, what's f of 2? F of n is an for all natural numbers. So what's f of 2? 2 being a natural number. F of 2 is a sub 2, right? So one more time, what's the area of this rectangle? It's this height, which is f of 2, and f of 2 is a2, we just talked about it, times 1. So this area is f of 2, which is a2, by this, right? Very good. How about this one? This rectangle, where this rectangle has also area, I should not say also, but this area is f of 3, right? Which is a sub 3 by this again. This rectangle has area f of 4 times 1, which is f of 4, and f of 4 is a4, and so on. And the last one is an, which is f of n, right? Okay. So from this figure, in fact, the ingredient that's needed to derive the star inequality is that the function is decreasing. As such, we can have that the sum of these boxes, the sum of these rectangles, which are a2 plus a3 plus a4 all the way to an, so it's compactly denoted by the sigma notation, this is certainly less than or equal to the area under this graph, right? The area under this graph from 1 to n, correct? So we're talking about the area, how about here I add this. So we're talking about the area bounded by 1, x equals 1, x equals n, and the function f of x and the x-axis. So we're talking about all this area under the curve and above the x-axis, and bounded below by 1 and bounded above by n, right? Certainly these rectangles are, the sum of these rectangles is smaller than this area, because we're missing some pieces, right? These not triangles, these anyway, these small pieces here. All right, so we have this inequality, and this holds for any natural number n, wherever you stop, correct? All right, on the right side, very similar situation, but now instead of looking at the right endpoint and creating the height of this rectangle being or one of the dimensions of the rectangle being the image of the right endpoint, this time around I'm going to take the left endpoint. So how am I going to create these rectangles? The first one is going to be still of one of the dimensions is 1, the length of the interval, and then the other dimension is going to be f of the left endpoint, which is 1 in this case, and f of 1 is a1, right? So f of 1 is a1, so the area here is a1. For this one, for the second box, or rectangle, one of the dimensions is 1, 3 minus 2. The other one is f of 2, which is a2. So this area here is a2, and this is a3, and so on, an, right? So we are overestimating the area this time under the curve, because we're adding those guys. So as such, we get this musical note inequality, right? We get that the area under the curve f, above the x-axis, bounded below by x equals 1 and bounded above by x equals n, so we're talking about this area here under the curve, is certainly at most the sum of these boxes, correct? And again, what's the active ingredient? The active ingredient is that the function is being decreasing. Okay. All right. Continuously decreasing, I should say. All right. Therefore, remember, we're trying to show part one. What's part one? If this integral is convergent, if the infinite region is finite, then the series is going to be convergent, right? Okay. So for part one, we are operating under this assumption. We're assuming that this guy is a finite number. Okay. So suppose this happens, then star provides us with the following. This is star, right? And this is for all n, correct? So I'm rewriting it. This is for all n again. And remember, f is a positive function. F is a positive function. So if you keep increasing n, ultimately reaching infinity, if you let n go to infinity, certainly this area is going to be at most this area, right? So you are adding these guys, this infinite region, to this finite region, correct? So certainly you're extending you're increasing that number, whatever this number is, you're increasing it, correct? Long story short, this number is bounded above by this number. Remember, this is a number. Why it's a number? Because I'm assuming that this is a finite thing. It's convergent. All right. So this last inequality, because the function f is positive. Therefore, if you add a1 to this side, to the leftmost entity in this compound inequality, if you add a1 here, you're going to get a1 plus the sum. So you're going to have a1 plus a2 plus a3 plus all the way to an. And what's that? It's the nth partial sum, right? So adding a1 here amounts to saying that this side becomes Sn. But this guy was at most this guy. So I'm going to add the same entity to both sides to get an equivalent inequality. So let's add a1 to this guy. So you get a1 plus this finite number, whatever this thing. I mean, it looks like, I mean, this improper integral is finite, right? Because it's convergent. This is the assumption. So this is a number plus a1, which is another number. So this whole thing is a finite number. Most importantly, it's independent of n. N has nothing to do in this business. Correct? So Sn is at most this number for all n. So the nth partial sum is bounded above by some finite number. And this is for all n again. Makes sense? So this is what I have so far. Very good. Furthermore, Sn is smaller than Sn plus an plus 1, right? Why? Because an plus 1 is fn plus 1. Why this is true? By the way, I'm talking about n being a natural number. Why this guy is correct? Well, this is one of the assumptions, right? I know that the image of any natural number is equal to a sub that natural number. Well, if the natural number is n plus 1, n being a natural number, so n plus 1 certainly is a natural number, f of n plus 1 is an plus 1. So this is why you have this, right? Okay, and since f is positive, that number is positive, but this number is an plus 1, so an plus 1 is positive. So from this side to this side, you add it by an plus 1, which is a positive entity. This clarifies why this inequality is true. Correct? All right, so since an plus 1 is positive, certainly this number is smaller than itself plus a positive number. And what is this guy? Well, Sn is the nth partial sum. Add to it the n plus first the n plus first term of the series. That becomes the n plus first partial sum, Sn plus 1. Correct? So long story short, you get that Sn is smaller than Sn plus 1 for all n. What does it mean? That this sequence Sn is non-decreasing, correct? Because any term is smaller than or equal to its successor. So it's a non-decreasing thing, and it's bounded above. So Sn, the sequence of partial sums, is a non-decreasing and bounded above sequence. Thus, by the monotonic sequence theorem that we talked about in the sequence section, that sequence is going to be a convergent one, correct? Non-decreasing and bounded above. Certainly that's going to be, by the monotonic sequence theorem, is going to be a convergent sequence. All right, but that being convergent, that's going to force the series an to also converge to that limit, whatever that limit is. That's going to be the sum of that series. Okay. So what did we show? We showed that if this happens, if the improper integral is finite, then the series has a finite sum. Makes sense? So that shows part 1 of the integral test theorem. For part 2, we're going to assume that this region is infinite. So this improper integral is divergent. Since f is positive, that means that this that the infinite region is infinity, which means that the limit as n goes to infinity of the bounded region from 1 to n of f of x dx, that's going to be infinite. Correct? Because the function is positive. All right, appealing now to the musical note. What's the musical note? This is the musical note inequality. Appealing to this, what does it say? It says that this bounded region, bounded above by f, below by the x-axis, and also by the two lines x equals 1 and x equals n, that's dominated by this guy. What's this guy? This is the Sn minus 1, correct? This is the sum of the first n minus 1 terms of the series. So this is Sn minus 1. So long story short, the musical note inequality says that this guy is bounded above by Sn minus 1 for all n. That's what I'm going to write here. Okay. And so since this happens for all n, at the limit, I'm going to still have this inequality holding for me. So I'm going to get the limit as n goes to infinity. So that guy as n goes to infinity, which I know it's plus infinity. We just discussed it, right? That guy as n goes to infinity, that guy goes to infinity. And this is less than or equal to this guy as n goes to infinity. Correct? All right. Since Sn is non-decreasing, why it's non-decreasing? We just said it. It's the same sequence. That guy is going to be smaller than Sn, and hence at the limit, this inequality is going to remain true. Okay. Remember, the sequence being non-decreasing means that any term of the sequence is dominating its predecessor, right? Okay. All right, so this means that this guy, the limit as n goes to infinity Sn, is greater than or equal to infinity, which means it is infinity, right? So it is infinity because this is always less than or equal to plus infinity. So that number has to be plus infinity. Okay, all right. And what does it mean that the sequence of partial sums is plus infinity? It means that the series is divergent. By definition, right? Because the sequence of partial sums diverges in a special way to plus infinity. All right, so the series that is divergent if you assume that this integral is divergent. And this completes the proof of the integral test, right? So we may use this test at our disposal at any moment we want. Okay. Comment. If we inspect closely the proof above, we may infer that when we use the integral test, it's not necessarily necessary to start the series or the integral at n equals 1. Remember, the integral here starts at 1 because it's the same one where the function is continuous, positive, and decreasing, right? That number 1. And that's the same thing where the sequence starts. I mean, if you inspect the proof, this is, all these ones are the same. Okay. Now, what this comment is saying, we don't have to have the 1. For example, if you want to examine this series, which starts at 5 when n is 5, it suffices to look at the integral from 5 to infinity, 1 over x minus 4 squared dx. Correct? So the corresponding improper integral starts at 5 this time. Well, why this is the case? Now we have the proof in front of us, so where was this one active in the proof? This one and this one and this one. Where was it active? It was active where we started graphing these blocks, right? So if instead of 1 you have 5, right? So you have f being continuous, positive, decreasing on 5 to infinity, or a number, some number, let's say 5 plus infinity, then you're going to start building these blocks from 5 onward, right? On the left picture and the right picture. And this means that's going to be 6. That's going to be the number plus 1, right? As for the left figure, and it's going to be, it's going to remain for the right one, it's going to still end at n minus 1, and this is going to start at 5, the number that we were given. So both of these inequalities are going to hold not for any natural number n, they're going to hold for any natural number that's at least 5, the number that we were given downstairs, right? Okay, and as such, you get that if, I mean, the same program applies. If the integral from 5 to infinity is convergent, you run the same program, but instead of 2, you're going to have 6. And I mean, it's the same thing. You're still adding by finitely many elements. And we get that the series that starts at 5 is convergent. Correct? Because the only one that you're going to be missing is a5, so you're going to add a5 to this side, because at the time it's going to start at 6. So add 1 to it, it becomes the first n terms of the series. And here I'm going to have a5 plus this finite number. The same thing applies, but the decorations are different. Instead of 1, I'm going to have only 5, and instead of 2, I'm going to have 6. So long story short, this remains true. This part 1 thing remains true. Now for part 2, if this integral from 5 to infinity is divergent, same thing applies. But here I'm going to write 5, but the same thing holds. And as such, you run the same thing all the way, but instead of 1, you're going to write the 5, and you're going to get the divergence of the series, but now instead of having the series starting at 1, technically I should write here 1, now it's going to start at 5. Correct? So if the series doesn't start at 1, don't panic. You can actually play the same game, but now the corresponding integral is going to be from that number onward. Okay. Furthermore, the function is not necessary to be a decreasing function always. What's sufficient is that the function is eventually decreasing, meaning there exists some number, let's say natural number, such that f start being decreasing on that interval n0 to plus infinity. It's the same game that we just discussed. Instead of having f being decreasing from 1 to plus infinity, you're going to have it decreasing from a certain point onward. So from a certain number n0 and not to plus infinity. And you can run the same program again, and what you're going to get is For part 1, you're going to get that the integral from n0 to plus infinity being convergent is going to imply that the series that starts at n0 is convergent. Now, if you would like the full series to be convergent, well, you just add, I mean, what's the difference between the series that starts at 1 to and the other series that start at n0? The difference is just finitely many terms, right? If the tail of the series, if the series that starts at n0 is finite, then certainly adding finitely many terms is going to remain a finite thing, right? This is one of the I think this was the last comment we made in the sequence section, the series section, the previous section. All right, and on the same note, if this integral from n0 to plus infinity f of x dx is divergent, you're going to infer that the series that starts at n0 is divergent, and hence if this is going to be divergent, certainly the full series that starts at 1 is going to be divergent. Correct? So what this comment is saying again is the one that appears in the theorem, in the integral test theorem, can be replaced by any number, let's say an integer number or positive integer, and you have to the corresponding integral is gonna the lower bound of the corresponding improper integral is gonna be actually that number that we're talking about, right? Okay. Also for the decreasing part, I mean, if it starts being decreasing at some point, that's gonna be the number that's gonna be the lower bound of that improper integral. Okay. Let's do an example. Let me just zoom in here. So the question is, test whether the series whose terms are 1 over n2 plus 1 and n starts at 1 is convergent or divergent. Okay? So test if the series is convergent or divergent. Well, the function f of x equals 1 over x squared plus 1 is a function which is continuous. This is continuous everywhere, right? This is a rational function whose domain is R, all real numbers. So continuity and being well defined are synonymous. Okay, this is continuous everywhere, in particular on 1 to infinity, and it's positive certainly for all x. This function is positive, correct? And lastly, this function is decreasing. Why this function is decreasing? I'm gonna write why and explain to you. Just fill in the details on your own. Why this is decreasing? How do we get our hands on that function being decreasing? Well, first test, right? First derivative test. So f prime, find f prime, and you're gonna see that f prime is gonna be negative. It's gonna be negative at on 1 to infinity at least, right? Okay. So all of these, actually, I should say, all of these happen on 1 to infinity. As such, I can employ the integral test that we just learned above. I can employ this. Observe that the f I'm constructing trivially verifies this. As such, the series that we are given, the series of 1 over n2 plus 1 that we were given, is convergent if and only if this is going to converge. The integral from 1 to plus infinity of 1 divided by 1 plus x squared is going to be convergent, right? So So the integral from 1 to plus infinity f of x dx, this is the limit as t goes to plus infinity of the integral 1 to t f of x dx. But look at f of x. F of x is 1 over x squared plus 1. So the integral of this is arctan, right? So that's going to be the limit as t goes to plus infinity of arctan of x between 1 and t, which is the same as the limit as t goes to plus infinity of arctan of t minus arctan of 1. Correct? All right. Arctan of 1 is pi over 4. And arctan of t as t goes to plus infinity, that's going to be pi over 2, right? So this is going to be pi over 2. So that's pi over 2 minus pi over 4, which is pi over 4, right? I don't care what the number is, to be honest, as long as it's a finite thing. Why this is useful? Because at this point we can just say that this is a convergent integral, improper integral. As such, the corresponding series is also convergent. So by the integral test it, the corresponding series is convergent. It's a finite thing, right? Agree with me? All right. Moving on. Example 2. For what values of real numbers p is the series 1 over np convergent? All right. So what should be p here for this series to be convergent, right? This is the question. Okay, so what happens if p is negative? If p is less than 0, what happens to 1 over n p? Well, this becomes n to power minus p, where p is positive this time, right? Where p is positive this time. Where negative p is positive, right? This is a positive thing. Oops. This is a positive thing. And as such, this converges to plus infinity as n goes to plus infinity, correct? So this number goes to plus infinity as goes to plus infinity. So what can you say then? What can you say about the series 1 over np? Well, the series is gonna diverge by what? By the test for divergence, correct? By the test for divergence, the test that we studied in the previous section. Remember, if a series converges, then its terms are eventually going to 0, right? The limit as n goes to infinity of its terms go to 0, is equal to 0 if it's convergent. So if this fails, if it doesn't go to 0, that's going to be divergent. Makes sense? So technically what I want to say here is I want to say that this guy, since this guy is not 0, that's what I want, right? Being infinity is not important to me. What's important is that it's not 0. and the test for divergence kicks in and tells me that the corresponding series, whose terms are these, is a divergent one. So far so good. Okay. If P now is 0, what happens? If P is 0, then we're talking about a series whose terms are, each term is what? Is 1, right? So 1 over NP becomes 1. Correct? And certainly this doesn't go to 0. This goes to 1 as n goes to infinity. And certainly 1 is not 0. So same thing, then the same conclusion follows. So that guy is also divergent by the test for divergence. Correct? Because the terms of the series do not go to 0 as n goes to infinity. Okay. Very good. What happens now if P is positive? So we dealt with P being negative. P is a real number. We dealt with P being negative, 0. Let's move on now to P being positive. If P is positive, well, what can we say about the function 1 over xp? So the function f of x equals 1 over xp. Certainly this is a continuous function away from 0. So is continuous away from 0. I'm particularly interested from 1 to infinity, right? So it's continuous on 1 to plus infinity. It's also a positive function there, right? It's positive there. Why? Because if x is bigger than 1, certainly it's x is bigger than 0, and raise it to power to any power, that remains positive. All right, and it's decreasing. It's decreasing also on 1 to infinity. Can you clarify why? I'm gonna let you figure. I'm gonna let you complete the details here, but obviously I'm gonna say why. So because if you look at the derivative of this function f prime, that's gonna be a negative, and f prime is gonna be negative on this interval, right? Okay. How do you get the derivative of this? Well, this is the same as x to power negative p. The derivative of this is going to be minus p times x to power negative p minus 1. Right? So you're going to get negative p divided by x to power p plus 1 as the derivative. And certainly this is going to be a negative function everywhere, let alone on 1 plus infinity. Okay? All right. So we got these three conditions verified for this function, and observe that f of n is 1 over np, which are the terms of the series for all natural numbers n. As such, if the integral from 1 to infinity f of x dx converges, and what's f of x here is 1 over xp, right? 1 over xp. Whenever this one is convergent, then the series is going to converge, the desired series, right? Well, this is something we've dealt with in the improper integral, the improper integral section, and we found that this is convergent if and only if p is bigger than 1, right? So this is what we found in the other section, in that improper integral section. Okay, so here to keep the flow going, I should say maybe however, this happens precisely when p is bigger than 1. And what I mean by this, it means, this is convergent if p is bigger than 1 and divergent if p is at most 1, right? And positive. In this case, positive, because we're talking about p being positive. But anyway, this is true for any p. Okay, so what do we get here? Thus, maybe a better word for instead of however, because all right, fine. Thus, by the integral test, um, the series 1 over np converges or is convergent precisely when p is bigger than 1, right? And is divergent if p is between 0 and 1, including 1. By the way, if p is 1, I know I can infer this by appealing to this property that we talked about in the improper integral, right? Section. But if p is 1, what the series is actually the harmonic series, which we know it diverges. Correct. So this is not really news to us when p is 1. All right. Okay, so let's summarize. If p is negative, the series is divergent. If p is 0, series is divergent. If p is between 0 and 1, the series is divergent. And if p exceeds 1, if p is exceeding 1, then the series is convergent. So what can we say? When p is less than or equal to 1, doesn't have to be positive. If you combine all three together, right? If p is at most 1, then the series is divergent. And if p is bigger than 1, then the series is convergent. So to summarize, let me summarize it in red. And this is an important result. Zoom in. By the way, this series is referred to as the p series. Okay, so this is called the p series. Let me write it for you over here. So this series is called the p series. Okay, people refer to this as the p series. Oh, by the way, this is part of the title of the section, right? So p series. And the conclusion is the p series is convergent if and only if p is greater than 1, right? Correct. So it turns out that the p series and this improper integral are of the same nature. They have the same nature. So whenever this converges, that converges as well for the same p's, right? Okay, remember the integral test only applies when p is bigger than 0, because that's the only time this function is decreasing. When p is negative and p is 0, in both cases, the function is not decreasing anymore. As such, the integral test is not going to be applicable, correct? So this conclusion was not expected, but it's a sheer coincidence. So this integral and this series, they have the same nature for any p. So it's a beautiful result. It connects the two. Very good. All right, example 3. This is a direct application of this conclusion that we just derived. Remember, how can we summarize example 2? The p series converges if and only if p is bigger than 1. This is the result of example 2. Let's apply it now. Take a look at this series. What are the terms here? The terms are the reciprocals of the square of natural numbers. Correct? This is how the terms of the series look like. All right, so this is a p series with p equals 2. As such, since 2 is bigger than 1, that's going to be a convergent series. As a matter of fact, the Swiss mathematician Leonhard Euler, who lived between 1701 and 1783, showed that actually the sum of the series is equal to pi squared over 6. So this has the precise result of this is actually pi squared over 6, and this is attributed to Euler. Okay. But what we just care about as far as this section is concerned, we just care about that this series is convergent. So this represents some number. We don't know what the number supposedly, right? Except if we read the pink thing. We know that this is going to be a number, but we don't know what the number is. And we know it's going to be a number because it's a p series with p equals 2. Okay. The next one, part B, this series, that's going to be a divergent one because p is half this time, right? P is half this time. Square root of n is n to power half. So it's divergent because p is smaller than 1 this time, right? Okay. All right, so the last example of this section is example 4. Determine whether the series whose terms are ln n divided by n converges or diverges. Well, to apply the integral test, we want to make sure that the function ln x over x is positive, continuous positive, and decreasing on some on 1 to infinity or on some subinterval of 1 to infinity, right? Okay, so let's take a look at the function f of x equals ln x divided by x. So this function is certainly continuous and positive on 1 to infinity. Correct? As long as we are bigger than 0, this function is continuous, and it's positive as x is bigger than 1 because ln x is negative when x is between 0 and 1, so this is correct. And how about the decreasing part? So let's check. Let's find f prime of x. This is the quotient rule, so I'm gonna get ln x, the derivative of ln x is 1 over x times x minus 1 times ln x divided by x squared. And this is the same as 1 minus ln x divided by x squared. Correct? Okay, so remember, for the integral test, I need f to be decreasing, so I need f prime to be negative. So f prime is decreasing. Okay, if and only if, I mean, the denominator is positive as long as x is bigger than 0. And upstairs, I need this to be negative for the whole thing to be negative, right? So we need 1 minus ln x to be negative. And this is the same thing as saying that 1 is smaller than ln x, which means if you apply the exponential function with base e, you get e less than e ln x, which is x. Correct? So f prime, f is decreasing. F is decreasing, which means f prime is negative if and only if x is bigger than e. Correct? All right. Thus, so what are you going to choose as the interval? I need a subinterval of 1 to infinity where the function is continuous, positive, and decreasing. Well, how about 3 to plus infinity, right? Remember the comment after the theorem, the integral test that we mentioned? The comment was, I don't care whether the function is always decreasing or not. What I care about is, it's sufficient. By sufficient, I mean the theorem, the integral test theorem, can be applied as long as the function is eventually decreasing, which means there exists some number from which on that function starts being decreasing. In this case, that n0 can be taken to be 3 because, as we found, the function given was is decreasing as long as x is bigger than e, and e is about 2.71828 or something, right? So I'm going to choose n naught to be 3. So thus, f is continuous, positive, and decreasing on 3 to infinity. Correct? So I can apply the integral test from 3 to infinity and infer about the corresponding series, which is going to be from 3 to infinity, right? Correct. Let me take you back to this. So I'm going to take the improper integral from 3 to infinity. I'm going to infer if that thing is going to be convergent. That's going to tell me that the series that starts at 3 to infinity is going to be convergent. But what I wanted, the question is about n being from 1 to infinity. Well, you just add two more terms to the series that starts at 3 to pick up the full series. Namely, you add a1 and a2. Right? a1 plus a2 plus the series that starts at 3 is the full series that starts at 1. Well, if that guy is going to be convergent from 3 onward, then the full series is going to be convergent. And now, if that improper integral is divergent from 3 to infinity, we're going to infer that the series that starts at 3 is going to be divergent. And if that series is divergent, it means that the limit doesn't exist. Adding a couple more entities, a1 and a2, to that, you're adding a finite number to a divergent series, certainly is going to be divergent. Correct? Remember, the concept here, divergence in this case means that the series is going to be plus infinity because all the terms are positive, right? All the terms are positive since the function is positive. Okay. So if you add a couple more entities, a finite number to plus infinity, that remains plus infinity, no problem. Okay, so it comes down to finding which case do I have, the part 1 or the part 2, and then we infer accordingly. Okay. Oops, right here. So we're gonna apply Sorry about that. Okay. So therefore, we apply the integral test for f of x equals ln x divided by x for x bigger than or being bigger than or equal to 3, right? Okay. Let's take a look at this improper integral. Well, by definition, this is the limit as t goes to infinity, plus infinity, 3 to t ln x divided by x dx, right? And what's this limit? What's this definite integral? So we're going to find this entity and then let t go to infinity after we find the expression. Well, this is of the form 1 over x times ln x dx. So this is of the form u du, right? If you think about u being ln x, du becomes 1 over x dx. So that's going to be the same as ln x squared over 2 between 3 and t, right? Because this looks like u du, and u du is the primitive of that is u squared over 2. All right. Now let t go to before that, let me write this using the first the fundamental theorem of calculus part 1. This is ln x or ln t squared minus ln of 3 squared over 2. Correct? And what happens when t goes to infinity, plus infinity? When t goes to infinity, this guy blows up. And the whole thing is going to be plus infinity at the end of the day. Correct? So long story short, this integral is blowing up. By the integral test, we get that this series that starts at 3 is divergent. And hence the full series, right? If the series is divergent, adding a couple of, adding a finite number to this remains divergent. So what am I going to add? I'm going to add a1 and a2, right? So I'm going to add when n is 1 and when n is 2. When n is 1, actually, this is a 0. Anyway, so then the full series is going to be divergent. Okay. Because if the full series converges, subtract a1 and a2 from a convergent one, that thing becomes convergent, which is a contradiction. As such, this must be a divergent series. Okay. All right, so this is the end of this section.